So good morning, everyone. It's a pleasure to have Naim Comar here today with us. So Naim completed his studies at the University of São Paulo, and he joined the institute this year as a postdoc in the Quantum Information and Quantum Matter group. He works with quantum information, quantum thermodynamics, and quantum foundations. And today it's a pleasure to have him here talking a little bit about his work. So thanks, Naim, for being here, and the stage is yours.
Okay, thank you. I would like to say thank you for everyone that is here present, and also for the first months I've been here, I was really well received, and it has been really nice to work here and having this serious and fun research. So yes, thank you very much. Everyone has made this environment really enjoyable. And so I'm going to present one of our recent works, and so it is named Contextuality in Anomalous Heat Flow. So I will first make the introduction, and the introduction I'm going to show some background about what is contextuality in anomalous heat flow, and I'm going to spend a lot of time in contextuality because I think most of people doesn't heard about it. And then I'm going to show the results. That is basically showing that we have signatures of contextuality in anomalous heat flow, and for future research that we are thinking about and advancing recently. So contextuality, I think that the main motivation is another way of looking to hidden variables. So the most famous way of studying hidden variables, as far as I know, is Bell's theorem, that we suppose we make three assumptions to obtain inequalities that must respect these three assumptions that are realism, that is supposing that there exists hidden variables explaining the statistics of quantum, of what we see in quantum labs, locality and freedom of choice. So this can be seen as an example where we have two parties, and we represent some hidden variables by a variable that we integrate out or make a marginalization, and we obtain the statistics that we see in the lab. And this is a famous inequality obtained by these statistics, that is CH-SH inequality. Of course, I'm not showing what is those operators and so on, but it's just to show that we have an inequality that is violated by quantum mechanics. And so the interesting thing is that this shows that one of these assumptions must be wrong. And of course, this was verified experimentally, and we know that recently gave a Nobel Prize. And contextuality is similar, is very similar, is the idea that we cannot have some kind of hidden variables. But here the hidden variables are seen that we suppose, when we say about non-contextuality, is that we are supposing that we have hidden variables independent of context. Contexts have a well-defined definition, but here I will just say that context means that we have statistics obtained by measurements of a set of compatible observables. So it's mainly when we have, for instance, this set here of observables, we have statistics that can jointly represent all of them. We can think of operators that commute in quantum mechanics, but this is theory independent. We don't need to assume quantum mechanics. And we have that each of these observables can have a relation of compatibility with other observables, so we have different sets of compatibilities. And the thing of contextuality is to show that we cannot have hidden variables that represent observables, well-defined values to these observables, before a measurement scheme, or globally describing all of these observables. So this is the main idea of contextuality inequalities or theorems of contextuality, not only inequalities. And just to show that how can we describe this as a mathematical form is, I just show this here just to you to understand that it's similar to the formulation of hidden variables in values inequalities. So we have like the probability of having some hidden variable and the probability of having an outcome from an observable given the value of the hidden variable. So we would just make a marginalization of it to obtain the statistics of the observables inside a set of compatible observables. So this is equivalent to having a global distribution for the values of the observables, therefore saying that we have some kind of reality predisposed to these observables. So I think a nice example is that in quantum mechanics we can relate this square here that is called sometimes magic square or Mermin square, that we have this matrix of operators here, and each row has a set of commuting operators or compatible operators, and each line also has a set of compatible operators, but globally they are not compatible. And for a hidden variable non-contextual model, we should respect this inequality. You can just write it down and convince yourself that this inequality is really simple if all defines of these observables are predefined. And we have that. You can also see that if you compute these observables, these averages for any quantum state, we violate this inequality. So I think this is a clear example of contextuality that is known as, in this case, of Mermin squared. Actually, Mermin-Petty square. And so this is the first time contextuality was put on in Cauchy-Specker contest. Actually, there's a Cauchy-Specker theorem that is quite general, and it is also in the 60s and almost a little bit later than Bell's theorem. And this for me, at least, is the most intuitive way of thinking of contextuality. You show somehow that you cannot have predisposed values independent of the context to observables. Then you can generalize it to obtain inequalities or proof of non-contextuality conditions to more general systems. And this is called generalized Speckens contextuality that we use on our work. It is a little bit, for me at least, a little bit more cumbersome, a little less intuitive. But the main idea is that in any experiment we have three procedures that are preparation, transformation, and measurement. And each of these choice of procedures that we choose in a lab is called the context. So instead of that set of observables, now the context is the choice you have in a lab. And an operational theory is any theory that describes outcomes for this set of choices of procedures. So quantum mechanics is an operational theory because we have is any theory where given this set of procedures you have an outcome probability, you can compute some outcome of probabilities. And there is a set of definitions needed here to define this kind of No, it's back. Thank you. So we have this definition of operational equivalence. That is mainly when the theory that we use, the operational theory, cannot distinguish between two processes. So is where we have this notion of operational equivalence. For instance, you have two different preparations in a lab are called operational equivalent if they satisfy an equality. They describe the same statistics whenever you have other schemes of transformations and measurements. So if you fix two preparations and can change any other kind of procedure, and the statistic doesn't change for this preparation, we say that it's an operational equivalence between preparations. A simple example, or the most important example in quantum mechanics, is that we have density matrices. So for density matrices, doesn't matter what kind of way that you prepare the density matrix. If it is the same density matrix, it will create the same statistics. So that's what we call operational equivalence. And we can have operational equivalence between transformations and measurements and so on. But here, just an example of preparations. And another definition is that an ontological model is something that describes underlying state of our physical system that can describe the statistics that we see in an operational model. So operational theory. So an underlying model could be some ontological model, could be some hidden variables model that respect the statistics of quantum mechanics that people can do, and where we are considering the operational theory quantum mechanics. So yeah.
Like the previous slide, you explained non-contextuality.
Yeah.
I didn't understand what's the difference with Bell inequalities. So it seems like you were just trying to. Well, non-contextuality seems to be like a requirement of having a hidden.
Yeah, it's a great question, because actually
hidden variable.
Yeah, it's actually non-locality is a kind of contextuality. Contextuality is more general, and hidden variables. Non-locality is a specific case where we are assuming that the operators are space separated, but it is the same idea actually. Yes, it's just a little bit more general. You don't require necessarily a space separation, and the thing of non-locality is especially the thing that we arrive at that situations when we have to choose if you want to have a hidden variable models, you have to let aside the locality. So this is nothing. This is something that is not necessarily wished here. So the idea here is more to show the impossibility of a previous value for the observables before the measurements. And non-locality is more about conflicting this with locality, right? Yeah, so the ontological model, for me at least, is a fancy name for hidden variables or latent variables. And we associate to each of the procedures a probability distribution that describes how the ontological model works with each procedure. So we have a preparation probability distribution for each preparation we choose. That is this me here. We have the transformation, that is a stochastic matrix, and the probability distribution for the measurement outcomes. And if you integrate it all out, we will arrive at the final theory that is the operational theory. So this all was suggested by Speckens, and now a lot of people study this. And finally, in this definition, we have for me, it's not a very direct definition related to Cauchy-Specker, but maybe I can show after if you want to ask me. It is Cauchy-Specker contextuality is a special case of this kind of non-contextuality. Sorry, Cauchy-Specker non-contextuality is special case of this non-contextuality. But in an ontological model, non-contextual models are a model where if you have an operational equivalence, like this one that I showed, you must have necessarily the same equivalence in the ontological description or in your hidden variables working. So if you have in the example that I show a preparation equivalence, you must have a probability distribution equivalence also. That actually means that the hidden variables behave quite the same way. And if this implication is not true, if you have a counterexample, you show that the theory is contextual. In this case, we call it preparation contextuality because the impossibility is shown for preparations, but we can have measurement contextuality and transformation and so on. And the Cauchy-Specker is a specific kind of measurement contextuality. So again, for me, this is not that direct. So, but you can ask later how we can make this connection. So, but this is to show that generalized contextuality is really a bigger scheme for seeing contextuality. And okay, why should we care? And so I think we could not convince this guy. Why should we care? Especially with foundations, but yeah. So in foundations of quantum mechanics, people turns to give some importance to this because, of course, non-contextual, classical systems must be non-contextual in the sense that we can have a phase space description for classical systems where the phase space parameters are the hidden variables, and but also contextuality is seen as a resource for several quantum protocols. So we have is seen as a resource for magic states or non-stabilizer states that our groups study here a lot, or quantum cryptography, random number generation, and so on, many other things. But and also we have like experiments for spotting contextuality, for seeing this as a resource, and also for the fundamental interest. And the first one was made with traped ions and neutron interferometry, but mainly today, especially, we have tests with photons. But our work is trying to show that we can spot contextuality also in some thermodynamic phenomena. Actually, our work is based in a result from Lostagro. Lostagro showed in his paper that you can have for some kind of qubit systems advantage for work extraction in work engines for heat engines. Sorry. When you have contextuality. So actually it is as an application for this, and we are trying to show that this could suggest that contextuality is also necessary research for certain thermodynamic phenomena. So this is what we wanted to show, and we show that it's necessary for anomalous heat flow. For some cases I had to complete here for all qubits interactions, but I should put that is not for any heat flow inversion that we can see in nature. So what is this heat flow and inversion or anomalous heat flow? So this is the idea mainly that we can prepare two systems in thermal states. So quantum systems in thermal states is just when you have a steady state of a system that thermalizes with a thermal bath, and locally they have a Gibbs distribution, and so we can think of a colder system and a hotter system. And if you put them in interaction, such that we can assume that they are isolated. They're quite well isolated from the surroundings. We can show that they respect a kind of Clausius inequality when we say that the energy exchange between them, we let them freely exchange energy, and we call it heat. And we obtain the inequality that we see, I don't know, since high school, that we have, if you have the system A colder than the system B, then you have beta A bigger than beta B, and we must have then A receives heat. And I think that the easiest way to think is just putting ice inside a glass of water. So we have the heat flowing from hot to cold. The heat flow inversion, or the anomalous heat flow, is just to consider that you imagine somehow you can maintain some initial correlations that we create between the two systems, but they are locally still thermal. So the partial trace of the systems are thermal state, but globally they are correlated. Then we can show that, and this paper has a nice proof of that, that we have inequality, a slight correction to Clausius inequality. That is that the variation, the change of the mutual information now makes the bound is not zero anymore. The bound of the heat times the difference of the inverse temperatures. So this means that if the systems start correlated, it can happen that if they start correlated, you can have the variation, negative variation of correlations. So you have consuming of correlations, and this negativity permits the possibility of a negative heat, and then you have the heat going from cold to hot. That is the anomalous thing. And it's not that strange in the sense that we are using correlation as a resource instead of using work as a resource, like we have in our refrigerators. We have a refrigerator that makes the heat go from cold to hot, but we are consuming work. Here we are just consuming correlations. At least as far as I know, that this was put firstly by Seth Lloyd, and this was experimentally made in for qubits in NMR setup in CBPF. And what we did in our paper that finally get into the results is that we prove a theorem where we can have an inequality of non-contextuality for the variation of some observable, and this variation is bounded by a quantity that, and the important thing of this quantity is that it is proportional to the square term of the time. So we generalize the theorem that Lostalio did, that was in this kind of form, but this was like a difficult theorem to apply to a larger set of physical systems. What we could show is that between any two energy conserving unitaries, between any two qubits with an energy conserving unitary, we can obtain this inequality. So this is our main theorem. We have to generalize the theorem to apply to this specific case. And the utility of this theorem is just one of them is to observe the variation of the heat based on this observable. So if you choose some observable, here we choose an observable, just the Hamiltonian of one of the qubits. We can show that you just put in the equation, you have that the variation of the Hamiltonian that we call heat in this case is bounded by this quantity. And So a non-contextual model actually must respect this inequality, and we have that in quantum mechanics. This is violated. The important things again about this term here is that it is of order of t squared, and g here is just the strength of the interaction. Actually, all these parameters here then depends of the kind of interaction, and we apply this to the most general case we could have between two qubits initially thermal. So if you have two qubits initially thermal, they can be correlated, and the correlation terms appear here. Actually, they appear here too. Here we have classical correlations, and here we have coherent correlations. And if you have the density matrix of two qubits, the partial traces here will be thermal states, and we show that for any case of this, we can have the heat term like this, and this is the standard form of the heat. That means then in the absence of correlation, we have the standard heat flow, because if beta A is bigger than beta B, this will be positive, and this is the term that makes possible the heat flow inversion, and also this is the term responsible for any coherent form of contribution to the heat. So this term, the important thing here is that this term is actually also proportional to t linearly, and we have the non-contextual bound of the linear of the inequality that says that if you have a linear term of the heat for small enough t, we can violate the bound, because the bound is quadratic. Just remember here. And just so, sorry. So for this last term, that is the responsible for the heat flow, is the same term that violates non-contextuality bound. So this term is the responsible for contextuality signature. Now, so yeah, this is the main conclusion. Actually, in our theorems, you have like a little bit more of situation where we can do that, but in general terms, we could prove to two qubits. So in any two qubits that interact isolated from the universe or surroundings, we have that anomalous heat flow necessarily imply contextuality, and actually not only anomalous heat flow, but any contribution for coherence imply contextuality. And as I said, we have here that this linear time dependence, but it can be not a good argument, because depending on this range here, or in the characters of the experiment, we may have that this time is incredibly small, so it could not be useful at all, or possible to see a time where this contextuality is violated in real experiments. So we want to find time interval where time intervals, we want to see that if these time intervals can really be reached in a lab. So we compare to the experiment that they made in CBPF, and actually is not that small time. The whole experiment is in the order of microseconds, and the violation happens into 0.18 microseconds. And we are trying to talk about with the experimentalists there to make an experiment to look directly to contextuality, so fix the terms so we can see contextuality for a bigger time, because the experiment, the main point wasn't contextuality, was the heat flow inversion. But yes, we think it is a reasonable time, at least theoretically. We're not considering the error bars and so on, so we want to put forward some experiment for it. So that there are the main conclusions of this first work. But we want to go forward and actually have a nicer explanation for what this means, because those inequalities that we use and the ones that we extended are always in this form. We have a variation of an observable bounded by some operators, or sorry, some function proportional to t squared, and that's it. And that means actually that we have a bound on the initial velocity of the system to change the observable. And this is normally related to what it is called in quantum mechanics of quantum speed limits. So this we have in quantum mechanics a nice relation between the variation of the change of some observable and the variance of a Hamiltonian. It makes sense because if you want to change some observable, you make your states is going to get out of eigenvector of the Hamiltonian if it is starting an eigenvector. So if you have a velocity in your dynamics of a quantum system, you must have some variance or uncertainty in the Hamiltonian. And this means actually we have a correspondence here to where non-contextual models cannot have a bound also for the variation of observables. So we want to see if we can have this kind of we can reach these speed limits only when we violate the non-contextual bound. So this is what is behind the heat flow inversion, because that kind of heat flow inversion says that we have a term that's really fast, and this term is a term that is not possible in non-contextual models. And just to a first hint that we had in related to this, in the same result of modern term is that it's a very known result and old result. They show that for a quantum system to start from some pure system and evolve to an orthogonal system, you have a minimum time to do it, that is equal to h bar divided by the variance of Hamiltonian. At the time and until today, people say that this is the real interpretation of time and energy uncertainty relations. But what we can do for some toy models is show that we have a bound dependent of this term G here, that is the strength of the interaction Hamiltonian that we have in some quantum systems. But this is done just only for some qubits or 2 qubits toy models. We want to generalize it to further terms, because actually one of our problems is that these inequalities here, they have a limited application scope. So we want to generalize it, and we have some ideas of how to do it, especially using some classical speed limits that exist, was discovered in the last decade. So we think that we can use these classical speed limits to make non-contextual speed limits, construct above it. So yeah, and in the conclusion, so we found inequalities to certify contextuality between any two qubits that interact with energy in conserving interactions. And yeah, and as a consequence, we show that contextuality is necessary for the anomalous heat flow inversion and compared to the experiment. And we are not working in generalize this, especially looking at some non-contextual versus quantum speed limits. So this is, I think, the next step in this kind of direction of research. So thank you very much, and thank you. Right.
Okay, questions?
So first, thanks for the talk, Naim. My question is very simple. When you say that contextuality is a necessary condition, is just for the system of 2 qubits, or
yeah, exactly. Yeah. That's a mistake that I did here in that slide. Yeah, it just for 2 qubits is necessary. Yeah, in this slide here, and yeah, for smaller, bigger cube systems, we don't know. We can show that for qubits, for some kind of interactions is necessary, but not for the general case. Yeah, that I should change this line here.
But thank you.
Yeah.
Thanks for the very nice talk, Naim. Actually, my question was very similar to what Vitor asked, because you have this statement that contextuality is necessary for anomalous heat exchange. But then it is also known that if you allow a memory system, for example, to mediate the interaction, classical correlations can also induce anomalous heat exchange.
Yeah, the thing is, I agreed. Actually, for larger systems, we have a Jennings result that we don't even need the memory. We have some closed system that conserves energy when non-coherent correlations can create anomalous heat flow in the energy eigenstates basis. But one interesting thing about contextuality is that depending on the base, coherence is not necessary nor sufficient to having contextuality. So coherence is of course related to the classicality, but is not direct, at least in non-contextuality way of seeing it. But yeah, the claim is, I think this claim was not good here in the presentation. Of course, in the paper we are more careful about it. But my suggestion in this case here is that the main problem is quite of technical, where when to deduce this kind of inequalities, we have to make some assumptions on the kind of interactions we can have. So the main difficulty of our work was to generalize it to 2 qubit sets, but 2 qubits is still very small. So that's why we are searching for generalized quantum speed limits for any non-contextual models, because I think that we could have best inequalities to test this for bigger systems. Now, about your question of considering an extra, a memory term in the interaction, that is something that we try to do in other work we try to make with a collaborator. And again, when the most difficulty is that when you put a system more a third system, we will now considering 2 qubit, at least 3 qubits interactions or bigger, then we cannot use these inequalities. So that's the main problem. We want to basically have more useful inequalities for bigger systems, and I think we must go for using other methods. That's why I think that looking to classical speed limits could be a better way. I don't know if I answered, but the thing is, we don't know actually if coherence or not having coherence is a good definition of classicality, at least in the sense of hidden variables. And the other thing is that with this theorem, we cannot use it for bigger systems. That's the main point.
So thanks for the talk, Naim. And what I wanted to ask was actually about the contextuality thing. So from what I understood, it is all about the preparation contextuality, I think.
No, sorry, no. Yeah, I just put preparation here because I think it's the more intuitive one to think about, because when we think about operational equivalence, we are seeing about this density matrix in general, but when you can have transformation equivalence when you consider the same CPTP maps, and you have measurement equivalence when you have the same POVMs. But I don't want to talk a lot of it, but the main violation here is about transformation contextuality that you use in our papers. But you can put the transformation inside the preparation to prepare a density matrix, so it's kind of related. But
yes,
that is the question.
Yeah.
The idea is to generalize to further steps inside a quantum experiment.
Thank you.
So I also have a question. So what is the measure of contextuality or non-contextuality in this anomalous heat flow?
The measurement non-contextuality?
The measure. So like which quantity tells you how much it is?
Okay. Yeah, there are research theories of contextuality. They are kind of recent and actually from last year, and I didn't read the paper until now, but you can define some kind of entropic kind of measurement of contextuality, especially the entropic distance to a polytope that defines the set of contextuality inequalities. But of course, this is very specific to the kind of situation we're analyzing. And there are trace distance, but it's actually a good question, because I think it's not easy at all to make a general definition of measurement of contextuality. So, yeah.
But in your particular model that you discuss, which parameter serves as kind of indication?
Say of an indication. Okay, the indication here is the difference between a signature or a witness of contextuality and a measurement of contextuality, or a measure of contextuality. But the signature here is to violate this inequality, in the same sense that you violate a Bell's inequality, you have signature of non-locality.
And which parameter controls that?
Okay. In our case, the parameter that controls this are these parameters here that depends on the interaction Hamiltonian that makes the interaction between the qubits. So in this experiment, they depend on the strength of the interaction that we have in this experiment, and the kind of interaction that is specifying on this term here. I think the actual number for this experiment that we are analyzing, this number is 2 here, and this is in the order of the energy of the interaction, and it is time dependent. So the thing is, you have the violation for a certain amount of time. So these are the parameters, and the thing of this figure here is to show that you have this violation. You have this violation for an amount of time, and then so this is the curve of the non-contextual bound of that inequality, and the violation happens during this time here. So yeah. So it's like an energy witness of contextuality, because the observable there is being measured here is energy in this case.
I'm a bit confused with the terminology, because I understood that actually contextuality is some kind of classicality.
Yes.
So whenever you have violation, it's non-contextuality. So you have a
sorry. No, it's the opposite. The non-contextuality is some kind of classicality, and contextuality is the quantum, because non-contextuality means that you don't depend on the context. The hidden variables may not depend on must not depend on the context of measurements that we are doing.
Okay.
It's clear.
So an ultimate question is like, how this is different from, I don't know, correlations in general, entanglement, or
this is
classicality. I don't know, other measures of classicality.
Yeah. So actually, this is more like a foundational question about what is classicality, because you can have correlations like correlations that explain Heisenberg uncertainty principle, something like this, explained by classical variables. You have like a noisy environment or a noisy experiment where you must have correlations caused by the experiment, or the noise caused by the experiment. And the thing here is just to try to make some definition that don't depend necessarily on the noise. You can, at least is my view of understanding it, you cannot have a model that in principle can be explained by a phase space trajectory, well-defined phase space trajectory like in classical mechanics, and by the addition of noise or some disturbing of the measurement, you have the correlations. So that's the main difference between correlations in general. So you show that some kind of weird correlations in quantum mechanics actually can be reproduced in classical models, but some of them not. That is the main idea. And so entanglement is an example of that. Entanglement is not sufficient to violate Bell's inequalities, for instance, and also contextuality inequalities. So it means that some kind of entanglements, you have toy models that show that you can have a classical model that imitates entanglement. So that's the main difference.
So could you go back to that slide where you had like a sine and psi squared and beta A and beta B? That one.
Okay.
So you said that the term in the first line was known before, and you added that red term, right? And beta A and beta B tells you like the difference in temperature from your hot and cold states, right?
Yeah. Mm-hmm.
So if you start with beta A equals to beta B, you could still violate with this term you added, because there's no temperature difference in the
exactly.
red part.
You don't have this interpretation, may not have of inversion of heat flow, but you can have the violations. Yes, you can suppose you can indicate some experiment where you have some kind of violation, time-dependent violation, where the temperature are initially equal. The thing is that comparing to thermodynamics, this maybe depend on who you're talking to, but maybe be not interesting because you don't have this inversion. But yes, you can have the violation. It's just a quantum system when you have a violation, if you think about it. And this term, yes, sorry, this is not new, actually, in the sense that it's just make a computation, and I think someone has done it. And in the inversion heat flow papers, they have this term here. They just don't show for the general case. We just show to the general case just to assure that for any case of two qubits interacting, we have this violation. But yeah, this was well known, I think.
More questions? Well, if not, let's thank Naim again.
Thank you.